Okay, everybody, welcome back to Nick's Algebraics. Today I'm going to talk about Taylor and Maclaurin series. But before I talk about that, let's review what power series are. So I'm going to get started by taking a look at a 1 divided by 1 minus x. Yeah, let's start with that. So what do you do to get 1 over 1 minus x? You got to do something all the way back from algebra called long division. So I'm going to I'll do that in the corner here. So I'm going to put the 1 here. And we're dividing this by 1 minus x. So you begin by dividing 1 by 1, and you get 1. And then you multiply. So you're going to multiply this 1 by the 1 minus x. So 1 times 1 is 1. 1 times the negative x is like negative x. And then we're going to subtract this entire thing. So what's going to happen is the 1s are going to cancel, of course. And then you have minus negative x. That becomes positive x. So that's the classic American long division algorithm. You divide, you multiply, and you subtract to get the remainder.
I have a question, Mr. Algebraics.
Yes,
Do you have to use long division, or can you also use synthetic for this?
it would be probably best to use long division in this case because the denominator has a larger degree, so it gets kind of awkward to use synthetic division.
All right, got you.
Yeah, wonderful question. So now you have to do you basically have like the remainder is x, so you have plus x. So now you do it again. You multiply. So you have x times 1 is x, and you do x times negative x is minus x squared. And then you subtract this entire thing. So you have x minus x, that cancels, and you have minus negative x squared, that's positive x squared. So that's the quotient, that's plus x squared. And I'll do this one more time. So I'm going to multiply. So x squared times 1 is x squared. And x squared times negative x is negative x cubed. And I'm going to subtract this whole thing. So again, the x squareds cancel, and you have minus negative x cubed. That's plus x cubed right there. And this just keeps going on forever. So it turns out that 1 over 1 minus x, it can be written as an infinitely long polynomial. It can be written as 1 plus x squared. Oh, no, 1 plus x squared plus x cubed, and so on. So yeah, oh yeah, go ahead.
Which values of x is this valid for?
Hmm?
Which values of x is this valid for?
Ooh, that's a wonderful question. So you might have noticed that this is a special kind of series called a geometric series because each term is x times the previous term. And we know that a geometric series converges if the common ratio, in this case, the common ratio is x because we're multiplying by x for each term. If the absolute value for the common ratio is less than 1, then this is going to converge. So this is where this equation is valid. So where absolute value of x is less than 1. So great question. And that makes sense because if x was like, 2, then you're just going to keep adding like 1 plus 2.
Right.
It's just going to go off to infinity. So, but if
Yeah, it
x,
just looks like something that would get bigger over time. So
absolutely.
it's unintuitive that it would be 1 over 1 minus x because that looks like a small looking thing.
Exactly. Yeah. But yeah, so this is a summation of infinitely many terms. If you write this in summation notation, you're going to get the sum. Let me make that look a little prettier. Yeah. I don't know why my sums are looking ugly.
Better
Yeah.
than mine.
We'll take it. So the sum of x to the power of n as n goes from 0 to infinity. So let's just double check that. Like you can see when n is 0, you get 1. When n is 1, you get x, and then x squared, x cubed, all that stuff. So this is very interesting because I was able to write this function here, 1 over 1 minus x, as a series in summation notation with x. So this is called a power series, basically like a series with a variable. And this is a representation of this function right here. That's what we say. So this is a function, and we call this the power series representation of that function. So that's the goal of today's video is we're going to learn about different functions and their power series. So we're going to look at like e to the x, for example, that has a power series. And yeah,
So can you just get the power series of any old function or only like certain ones?
well, not everything has a power series representation at a particular like point because there are functions that are like discontinuous at some points. So for those kind of functions, then you can't create a power series representation like at that center where centered at where the discontinuity is.
Okay, gotcha.
Yeah. So, but for today, of course, since it's a power series video, um, everything we're gonna do is gonna every function we're gonna deal with is gonna have a power series representation. That power series representation may not be valid everywhere, like because you can see right here, this is only valid when the absolute value of x is less than 1. But it's a representation still. It's better than nothing. So let me formally go tell you guys what a power series is. Let me highlight this because it's really important. So a power series is any series in the form of like the sum of a sub n times x minus c to the power of n as n goes from 0 to infinity. So we typically begin the index of a power series at 0. And in like previous lessons, you might have like started the index at 1, but for a power series, we typically started at 0 in general. But at the end of the day, you're free to choose whatever value you want to start it at. There's no restriction on that because it's just an index. As long as your nth term is correct, you can begin n at any value. So a sub n, those are the coefficients, and x is the variable of the series. And we have, yeah, minus c to the power of n. And c is the center of the power series. So if you expand this, starting n at 0, then when n equals 0, you're going to get a sub 0 times x minus c to the power of 0. And x minus c to the power of 0, that's just 1. So you just get a sub 0 for your first term. And when n equals 1, you get a sub 1 times x minus c to the power of 1 right here. And you'll get, of course, when you plug in 2, you're going to get a2 times x minus c squared, and so on. So, and yeah, that pattern goes on forever. And so yeah, this is the general form of a power series. And like I said earlier, a sub 0, a sub 1, a sub 2, those are called the coefficients. And a sub 0 is called the constant coefficient because it doesn't have any x attached to it. So, and like I said, C is the center. And this C, you can think of it as like the shift. So you learned about shifts back in algebra. So like for example, if you had like kind of like an f of x minus h situation, like h would either shift the function, the graph of the function to the right or to the left. So for example, if you uh, want to graph the function f of x equals x minus 2 squared, this is just a parabola. And it's shifted 2 units to the right. So your vertex is going to be at, let me just put my x and y axes. It's going to be at 2 comma 0 like that. So yeah, you can
So
think of
bubble.
exactly, very beautiful. And so yeah, you can think of the center as like the shift in a way. But today I'm going to mostly focus on the center being 0 just to keep it simple. So for
This
this
is name for that, right?
yes, there is a name for that, and I'll talk about that in the next couple of pages. So for this series, um, all the coefficients are 1, because it's 1 plus 1x plus 1x squared. Like the a0, a1, a2, those are all 1. And the center is 0 because it's just x to the power of n. It's not like x minus 2 to the power of n or anything like that. So yeah. But yeah, this is a very useful power series, very, very useful power series, because from this power series, we can derive power series of functions that are in this form. And that's what I'm going to do in the next example. So for this example right here, it asks to find a power series representation for f of x equals 1 over 3 plus x. And notice how I'm saying find a power series representation.
I did notice that.
Yes, and there's a reason for that. It like meaning that there can be multiple power series representations for a function. Like if a function can be represented as a power series, that power series is not unique because you can come up with power series with different centers. So that's why I wrote a power series. So I'm going to, you know, choose the center to be 0 just to keep it simple, and that will be a power series representation of this function. So, you could absolutely do long division like I did last time, but I'm gonna show you an easier way. Like, notice how this function right here can be written in this form. Like, we can rewrite it as 1 over 1 minus something. But the problem is instead of 1 minus something, it's 3 plus x. Like, I want this 3 to be a 1, and I also want x to be subtracted. I don't want plus x. So, let me just rewrite this right here. So we have f of x equals 1 over 3 plus x. So to make this a 1, I'm going to factor out a 3 from the denominator. So I'm going to put equals 1 over, and when I factor out the 3, this becomes a 1, just like I wanted it to be, and then plus x over 3. And you can check that this is equal to this by, distributing. You'll get 3, and then you'll get back the x. But now the issue is how do I make this a minus? So,
Idea.
yes, what do you think?
1 minus negative x over 3.
Yes, exactly. We can write that positive, whoops, as a double negative. So I'm just going to duplicate this. So I'm going to say 1 minus, and here, just so I don't have a bunch of parentheses, I'll put this like 1/3 out here like that, like that.
It's beautiful.
Absolutely. So yeah, we have 1 over 1 minus negative x over 3. So yeah, we're writing it as a double negative.
I can see where this is going.
Yeah, so
So,
some
like, when you use the summation notation, instead of x to the n, it's negative x over 3 all to the n, right?
exactly, we're going to use this. And exactly like you said, instead of x, we have negative x over 3. So this equals 1/3 times the sum of negative x over 3 to the power of n, as n goes from 0 to infinity. All right, and we're pretty much done. But what I'm going to do is I'm going to rewrite this so I can easily identify the coefficients and all that stuff. So if you want a formula for like the coefficients, you need to like separate each factor. So what I'm going to do is I'm going to raise like the numerator and denominator to the power of n. I'm going to use my exponent properties. So this is going to become, I'll do it like this. I'll say negative 1 to the power of n over 3 to the power of n times x to the power of n. And then we have that 1/3 in the front.
So we could just make in the denominator 3 to the n plus 1.
Exactly, that's right. Using our exponent properties, that 3 to the power of n in the denominator can become 3 to the power of n plus 1.
And I
So
see this alternating, right? So since we had like 1 over 3 plus x, if it was like plus x, you have to make a double negative there. So is it going to be alternating every time you have like 1 over something plus x?
typically, yeah, because it's gonna have that minus in there, and we're gonna raise it to the power of n once we use this power series like formula. So yeah, that's where that alternation of the signs comes from. Yeah, this is it. This is a power series representation of 1 over 3 plus x. So again, I wrote it specifically in this way because now I can see what my a sub n is. Like I can see these are going to be my coefficients. And of course, like the center is 0 because it's just x minus 0 to the power of n.
Just for the people at home, could you show what it would look like if it were centered at some other number? Like, I don't know, 2 or something?
Um, no. Yeah, center is going to be 0 for pretty much all these problems. Okay. So this is great, but what if someone asks you to come up with a power series for sine of x or cosine x or e to x?
Yeah, I could
Or
ask them.
exactly. Like what if you need to come up with a power series of a function that's very difficult to rewrite in this form? So so the real question is like how does someone come up with those kinds of power series? Like where do they come from?
Magic.
Maybe you'll see. So here's how. We're gonna assume. So let's say you have a function f of x and you want to derive its power series. So we're gonna assume that f of x has a power series representation. And so what this is assuming is that our function, like whatever the function is, e to the x, sine of x, 1 over 1 minus x, whatever it is, we're assuming that it can be written as uh, a naught plus a1 times x minus c, plus a2 times x minus c squared, and so on. But the question is, like, what are these numbers? Like, what are these coefficients here? So that's the goal of the problem, is to find those coefficients. And it's actually pretty easy to find those a's. If you want a sub 0, all of these terms right here, they need to go bye-bye.
Yes,
So
yes, you do. You need to die.
exactly. So what do we need to do to make these terms disappear? I need
Yes.
Oh, maybe. We need to let x equal c. You can see that when you let x equal c, all of these terms will vanish, and you'll be left with the a sub 0. So so that's the first step, is let's find f of c. So f of c, if you plug that in, you're going to get a sub 0 plus a1 times c minus c plus a2 times c minus c squared. And hopefully you'll see the pattern from here. You'll see that, like, all the terms except for a sub 0 die.
They
So
went bye-bye.
exactly. So we get that a sub 0 is just f of c. So let me put that in another color because it's important. So we found the first coefficient. So next up, we need to find a1 now. So again, we want uh, this term to survive and the rest to become 0. But it's a little different this time because last time a0 was a constant, and when you plug c in, everything went away except a sub 0. But now I want this to be a constant.
You want it to just be A1.
Exactly. So any
If only we knew some mathematical way to reduce the power of polynomials.
I know, exactly. So we
Maybe
need
there was a power rule or something that we knew from differential calculus.
yes, we're gonna use this magical thing called a derivative. So
Oh, derivatives.
yes, very scary word, but it's gonna save our lives today. So not the not these terms lives, but it'll
Those
say
went bye-bye.
yeah, it'll save the a sub 1. So yeah, so what we're gonna do is we're gonna take the derivative. And if you take the derivative, uh, a sub 0 is a constant, so that's gonna go away. And um, a1 times x minus c is just gonna become a1 because of the power rule. Yeah, and
So I feel like we need an f prime of x,
we do. So yeah, let's find f prime of x. Let me write that down. So f prime of x.
or an f prime of c anyway.
Yeah, we'll take the derivative and then we'll plug in c separately. So so this is f of x, so I'm gonna take the derivative of this. So a0 is a constant, it's gone. Using the power rule, this becomes a1 plus, and then over here, this becomes, this 2 goes out to the front, so you get 2 a2 times x minus c, and I'll do like I'll do the other 2 as well. So and then the other one becomes 3 a3 times x minus c. So using the power rule again, that 3 will move out to the front, and then plus 4 a4 times x minus c, and so on.
What happened to the exponents?
Oh, that becomes oh, silly me. So x minus c squared and then x minus c cubed.
We should probably note that there is chain rule going on here, but since like the derivative of x minus c is just going to be 1, you don't really see it. But
Yeah, that's true. You're right about that. But yeah, so yeah, don't forget to subtract 1 from the exponent. Yeah. For this one, I just got away with it because the 2 just went in the front and became 1, and then I kinda applied that logic to the others, but yeah, you gotta subtract 1. Okay, so just like last time, I'm gonna, plug in c into this derivative. So f prime of c equals a1 and then plus 2a2 times c minus c plus 3a3 times c minus c squared. And you guys can see what's happening. Like,
they go bye bye.
exactly. These go bye bye. And you're left with f prime of c equals a1. So that's our next coefficient is a1 is just f prime of c. All right, cool. So now for the second coefficient. I'll do A2 and A3 and then hopefully we'll get the pattern by then. So for the second coefficient, it's the same idea. I want this to be a constant. I just want A2. So
Second derivative ought to do the trick, I imagine.
exactly. So now we're going to take the derivative of the derivative. So right here, this is going to be f double prime of x. So this equals, so this becomes 0 because it's a constant. This becomes just 2a2 plus, again, like power, well, chain rule specifically, but like um, bring this 2 to the front. You're going to get 3 times 2a2 times x minus c. I'm not writing 6 because like it's suggestive of something that I'm going to talk about soon. So
This video flagged. It's too suggestive.
yeah. So and then the next derivative is uh 4 times 3 a4 times x minus c squared, and so on. So that's the second derivative. So now let's plug in c. So f double prime of c equals, so we have 2a2 plus 3 times 2a2 uh, times c minus c. And you guys know what's going to happen. Like the others are just going to, zero out.
Math murder.
Exactly. So that's gone. So if you solve for a2, you're going to get that a2 is f double prime of c divided by 2. So a2 equals f double prime of c divided by 2. And specifically, I'm going to write 2 factorial. And you guys will see why later. That's why I'm writing this as 3 times 2, because that's really, notice that 3 times 2 is really 3 factorial. It's the same thing as 3 times 2 times 1. Yeah, let's do one more. So it's the same thing. We want a3, so we need to differentiate the second derivative. So f triple prime of x equals, so this is a constant, so that's gone. This becomes 3 times 2a2, and oh, wait, this should be an a3. I wrote A2 twice. This is A3. So
Gotta
yeah,
cover your tracks if you're gonna commit math order.
yeah, that's a I mean, luckily it just died off, so it didn't matter. But yeah, that should be an A3, guys. That was just a joke. All right. So 3 times 2 times A3. And then the derivative of this right here is plus 4 times 3 times 2 A4 times x minus c. So um notice that this is like a 4 factorial right there.
I did notice that.
Yeah, so we're going to plug in c just like last time. And, the first term stays the same. And you're going to get 4 times 3 times 2 times a sub 4 times c minus c. So this is going to, oh yeah, and by the way, this goes on and on. And because that's just the triple derivative. And then this is going to cancel right there. Yeah, and this goes on and on as well. All right, so now we can solve for a3. You just divide by the 3 times 2. So you get a3 is the third derivative of f at c divided by 3 times 2, which is 3 factorial. All right.
I
So,
see it has emerged.
yes, a pattern has definitely emerged. So, what would you say in general the nth coefficient is equal to? If I were to figure out like, so in general, we know that a sub n, what does it look like it equals? Like,
Well, it looks like the nth derivative of f at c
mhm,
divided by n factorial.
exactly. So the nth derivative, we put like a superscript in parentheses like this because we can't just keep using prime notation forever. And yeah, over n factorial.
That looks like a formula for coefficients if I ever saw one.
Yes, absolutely. Okay. So yeah, that's the nth coefficient. It's equal to the nth derivative at c over n factorial. And that makes sense because you can see a2 is over 2 factorial, a3 is over 3 factorial. So of course, a sub n is going to be over n factorial. All right. So this uh, gives us what's called the Taylor series. So assuming f has a power series representation, uh, then f of x is equal to the sum of the nth derivative of f at c over n factorial times x minus c to the power of n. So if f of x has a power series representation at c, then that power series is going to be the Taylor series centered at c. So that's really important. So I'm going to highlight Taylor series. Yeah, and this is what it is in expanded form. You can see if when n is 0, you have 0 factorial is 1, and this is x minus c to the power of 0. So you just get um the 0th derivative is, just the function. So it's just f of c. And then when you plug in 1 for n, you have 1 factorial is 1, x minus c to the power of 1, and you have the first derivative, so times f prime of c. So we're assuming that this function is infinitely differentiable. So all of its derivatives exist. And that's what this part is saying. When we're assuming that the function has a power series, then we're really just assuming that it's infinitely differentiable.
I'd also like to point out that for the f prime of c term, since that's where n equals 1 for the first derivative, you're really dividing by 1 factorial as well. And for the f of c term also, it's like the 0 with derivatives here divided by 0 factorial. Since those are both just dividing by 1, I don't really write that, but it just keeps the pattern for
Yeah,
those who like to see that.
that's right. Yeah, this is really like over 0 factorial and this is over 1 factorial. Exactly. But those are both equal to 1, so we don't write it. Even though, yeah, it makes the pattern like more obvious. Yeah, and then that also leads us into something called the Maclaurin series.
I can never spell that for some reason.
Yeah, this is Maclaurin's a funny name, so it's just the Taylor series with c equals 0. So just, it's convenient. So, and again, we're assuming that f of x has a power series representation. So yeah, and all of the problems that we did can be done using these formulas now. Well, and I mean specifically this formula because we centered everything at 0. But you can check, like you can redo these problems here using this Maclaurin series formula, and you'll get the exact same answer. So, so you don't have to get the answer uh, using an already known power series anymore. So that's how magical these formulas are, and that's how easily we found these coefficients just by like taking derivatives and plugging in c. So let's do an example. So let's find the Maclaurin series for f of x equals e to the x. So let's find the coefficients. So we need f of x and all its derivatives. And this one's pretty easy because all its derivatives are just itself. So we have f of x equals e to the x. F prime of x is also e to the x.
I'll never guess what f double prime is.
Yeah, and then magically f double prime of x
Spoiler alert.
is, yeah, spoiler
Yeah.
alert, e to the x. And I'll just do one more. F triple prime of x is also e to the x. And then I'm gonna, since this is a Maclaurin series, I'm gonna plug in 0 because that's the center. So f of 0, e to the power of 0 is just 1. F prime of 0 is also 1. F double prime of 0 is 1. F triple prime of 0 is 1. So I'm just gonna start off by just writing those out because we're gonna
It
use.
was really hard.
Yes. So so now I'm gonna plug it into this formula right here. So let me just write it out again. So f of x equals f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and so on. So yeah, now we're just going to plug everything into this formula now. So we know f of x is e to the x. F of 0, I did that right here, that's 1. F prime of 0 is also 1. I'll just write it out, 1x. And then f double prime of 0, also 1. So we have 1 over 2 factorial times x squared. F triple prime of 0, that's right here, that's also 1. So that's 1 over 3 factorial times x cubed, and so on. So if you write this in summation notation, you'll get that e to the x is the sum of x to the power of n over n factorial as n goes from 0 to infinity. Right, and you can check because this is x to the power of 0 over 0 factorial, that's just 1. X to the power of 1 over 1 factorial, that's just x. And over here we have x squared over 2 factorial. Over here is x cubed over 3 factorial. So, so that's the Maclaurin series for e to the x. It's just x to the power of n over n factorial.
One thing that I think is really cool about this is that, like, obviously it's an infinite series, but if you like cut off some of the later terms to like stop it at x cubed, you can get a pretty good approximation for e to the x.
Absolutely, you'll get a nice cubic approximation, which I'll talk about near the end of this lesson. All right, so let's move on. So let's find the Maclaurin series for sine of x. So we want the power series representation of sine of x, basically. And again, this is the same thing as the Taylor series centered at 0.
So the first part of a problem like this is always calculating some derivatives, right?
Absolutely. We're going to start off with the function, and we're going to take derivatives of it. This one is going to be, this one's pretty easy as well, but it's not as easy as e to the x because it's not going to be the same thing every time. But you'll see there's going to be a bit of a pattern with the derivatives of sine of x. So f of x, that's just sine of x. All right. And then f prime of x, the derivative of sine is cosine of x. F double prime of x equals negative sine x. F triple prime of x equals negative cosine x. Uh, I'll do 3 more, I think, because we're gonna need a couple for this. So f, the fourth derivative, I'm gonna stop using primes now, is the derivative of negative cosine is positive sine. And the fifth derivative, we're back to, you know, now you can see we're back to the first derivative. It's cosine x. And then one more, the sixth derivative is negative sine of x. So the derivative is repeat, of course. So after every 4 derivatives, you get the same thing. So the derivative is periodic. So I think, yeah, that's more than enough derivatives. So now we're gonna center these at 0. We're gonna plug in 0 for all of these. So
Unit circle time.
yep, tons and tons of unit circles. So we have sine of 0. That is 0. We have f prime of 0.
Cosine of 0 is 1.
Yeah. And then f double prime of 0. We have negative sine of 0 is just 0 again. And then f triple prime of 0. We have negative cosine. So negative cosine of 0 is negative 1. And then the fourth derivative at 0, that's sine of 0, which is 0. The fifth derivative at 0 is cosine of 0, which is 1. And lastly, the sixth derivative at 0 is negative sine of 0, which is 0. All right. So notice how all the even derivatives, like the second derivative, the fourth derivative, the sixth derivative, are 0. And
I do notice that.
yeah, and all the odd derivatives survive, as we can say. So and
So
even
it's between 1 and -1.
yeah. And that makes sense because sine is an odd function. This has something to do with like sine being an odd function. So I'm gonna bust out the Maclaurin series formula just like last time. So let me just duplicate this. And I'm gonna plug everything in. So f of x is just sine. F of 0 is 0. I'll just write it out. 0 plus, and then f prime of 0 right here, that's 1. So we have a 1x plus f double prime of 0. It's an even derivative. We saw that right here. So it's 0. I'll just write the whole thing. 0 over 2 factorial times x squared plus the third derivative at 0 is -1. So that's -1 over 3 factorial times x cubed. And if you keep going, you'll get like the fourth derivative, which is 0 over 4 factorial times x to the power of 4, plus the fifth derivative, which is 1. So 1 over 5 factorial times x to the power of 5. And the sixth derivative we saw right here, it's 0. At 0, the sixth derivative is 0. So we have 0 over 6 factorial times x to the power of 6, and so on.
I see there's gonna be some murder here.
Yeah, lots of math murder going on right now. So you can see like this is gone, this is gone, and this is gone. And of course that 0 is gone too, right there.
Everything even died.
Yeah, exactly. So and the sign is it looks like it's also gonna alternate. So we're left with x minus I'm gonna put the x cubed in the numerator. So minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial. And I don't have the next one, but like you can guess it's going to be minus because it's the sign's alternating. Let me bring that minus a little higher. So minus x to the power 7 over 7 factorial. So
And
yeah,
that goes on and on.
exactly. And so let's write this in summation notation. So it's a little bit more complicated than last time. So we have the sum. So this is alternating. So what I need to do is I need to slap on a -1 to the power of n. That will take into account the alternating signs. Because you can see when n is 0, you'll get this will -1 to the power of 0 is 1. So that's positive. And then -1 to the power of 1 is negative. -1 squared is positive. So that'll, you know, deal with the alternating signs right there as the -1 to the power of n. And we also have these odd factorials. These are in the denominators, we have these odd factorials. And this is really like a 1 factorial here, which is 1. That's why I didn't write it down. But these are odd positive number factorials, and odd numbers can be described by 2n plus 1. So I'm going to have -1 to the power of n over 2n plus 1 factorial. And you can check, like if n is 0, here, let me just write down that we're doing the sum as n goes from 0 to infinity. So when n is 0, you get 1 factorial, which is consistent with the first term because it's x over 1 factorial. If you plug in 1 for n, you get 2 times 1 plus 1, which is 3 factorial, so that's consistent with the second term, and so on. And the exponents are also odd, so I'm also gonna put, times x to the power of 2n plus 1. Same thing as the factorial in the denominator. And there we go, that's the Maclaurin series for sine of x.
would also point out that a lot of Calc 2 classes would expect you to have e to the x and sine of x and cosine of the x all memorized. They're their Maclaurin series.
Exactly. Yeah, this is a must-know power series. It's one of those power series you have to memorize. But it's an infinitely long polynomial, and, again, sine is an odd function, so that's why we have, all these odd exponents and stuff popping up. So, let's do the next example, the Maclaurin series for cosine of x. So, again, this is a Maclaurin series, so it's the Taylor series centered at 0. And you can do the exact same thing as last time, pretty much. And you can use the formula and all that stuff. So that's one way of doing it. But you can also get the power series for cosine using the power series of sine of x.
Ooh,
Yeah,
this is trick.
yeah,
This is a magic trick.
yeah. We're gonna do a little
Let's do the derivative.
exactly because sine and cosine are related because they're derivatives or they're antiderivatives of one another. So I'm gonna write that cosine is the derivative of sine of x, and I'm just gonna plug in the Maclaurin series for sine. So this is gonna be the derivative of this whole thing right here. All right, so now we just need to differentiate. So since we have a polynomial, like an infinitely long polynomial, we just have to take the derivative term by term. So the derivative of x using the power rule, that's just 1. And uh, using the power rule again, you get, for the second term, you get 3x squared over 3 factorial. And I'm going to write it a little bit differently. I'm going to write it as 3 times 2 factorial because you're going to see like some things are going to cancel. But one thing I guess I should mention is that you should not be using the quotient rule for these derivatives because, yeah, we're dividing, but we're dividing by a constant. So remember, like when you're taking the derivative of f of x over c, for example, that's just going to equal f prime of x over c because of the constant multiple rule. So yeah, you don't need to use quotient rule. We're just going to use power rule. But yeah, let's keep going. So we have plus, again, this is going to become 5 times x to the power 4. And I'm going to write 5 factorial as 5 times 4 factorial. And then minus the derivative of x to the power 7 is 7 times x to the power 6 over, and then the 7 factorial I'm going to write as 7 times 6 factorial, and so on. So let's cancel some stuff out. So I'm going to cancel this 3's and the 5's and the 7's. And you're going to be left with 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial minus x to the power 6 over 6 factorial, and so on. And notice how all the exponents are even, and that makes sense because cosine is an even function. So we would expect like the polynomial itself to be an even function with all those even exponents. So we're basically done. Now we just have to, let's just write this in summation notation. So this equals the sum of something as n goes from 0 to infinity. So the signs are alternating just like last time. So we need -1 to the power of n. In the denominator, I see 2, 4, 6, 8, and so on. So those are even values, and they can be described by 2n. So this is going to be over 2n factorial. And same thing with the exponents. The exponents are 2, 4, 6, and like they're even, so it's times x to the power of 2n. And that is the Maclaurin series for cosine of x.
And I'd like to repeat again that e to the x, sine of x, and cosine of x are those three Maclaurin series you want to have memorized, usually for Calc 2.
Absolutely. It's a all yeah, all four of the power series we saw so far, those are a must know. So e to the x, sine x, and 1 over 1 minus x. Yeah, those are,
Geometry.
yeah,
So, like, if you wanted help memorizing these three we did, and you can notice that like sine and cosine respectively look like the odd and even parts of e to the x, except sine and cosine like they alternate, where e to the x does not alternate.
exactly. Yeah,
And I think we'll be doing an exercise very soon that might help remember that.
absolutely. Yes. So there's a relationship between sine, cosine, and e to the x. So the cool thing is that if I differentiate their power series long enough, I get their power series back. So for example, if I differentiate cosine of x 4 times, I'm going to get cosine of x back. So sine, cosine, and e to the x have this nice property that their derivative is periodic. So we're going to take a look at a problem that relates these three wonderful functions. So that's the next problem: is find the Maclaurin series for f of x equals e to the power of ix. So before I start this problem, I'm going to review some stuff about imaginary numbers. So we know that I is the square root of -1. You know, it's the building block of all those imaginary numbers. And I squared is just the square root of -1 squared. So the squared and square root are going to cancel out, and you're just going to get -1, which is, a real number. And I cubed is I squared times I to the power of 1. So I squared is -1, so -1 times I is just negative I. And I to the power of 4 is I squared times I squared, which is -1 times -1, which is +1. And let's do one more, I to the power of 5. That's the same thing as I to the power of 4 times I to the power of 1. And I to the power of 4, I said earlier, that's just 1. So 1 times I to the power of 1. Here, I'll write it out. 1 times I is just I. So it's like repeating again. So, and you'll see like, and this keeps going on. If you can keep going if you want, and you'll see like I to the power of 6 is going to be the same thing as I squared. It's going to be -1.
It's like how like sine and cosine, they all like the fourth derivatives, they repeat after every four derivatives, right? So I repeats after every four powers, which is very interesting.
Yes, very, very interesting.
What that might lead to, who can say?
Yes. Let's take a look. So again, we're trying to find the Maclaurin series for e to the ix. So we have the Maclaurin series for e to the x. So let me actually copy paste that right here. For e to the ix, all you have to do is take the power series for e to the x and replace x with ix. Like, that's pretty much it. So e to the ix is going to equal 1 plus, so x is being replaced with ix now, so this is ix plus, I'm going to put this x squared in the numerator, and it's going to turn into ix squared over 2 factorial plus ix cubed over 3 factorial. And let me write out a couple more terms. Plus, if you keep going, you're going to get ix to the power of 4 over 4 factorial plus ix to the power of 5 over 5 factorial plus ix to the power 6 over 6 factorial, and that should be good enough. So we have powers of I. When you have even powers of I, like we saw last time, you're either going to get -1 or +1. And because you can see I squared is -1, I to the power 4 is +1. And for odd powers of I, you're going to get, an imaginary answer because, for example, I cubed is -I to the power 5 is I, and so on. So let's simplify that now that we know that. So 1 plus ix, that we can't do anything to that. Over here, for this term, we have ix, that quantity squared. So that's just I squared times x squared, and I squared is -1. So it's just going to be negative, so like minus x squared over 2 factorial. And for this term, I cubed is just -I, so this becomes minus I x cubed over 3 factorial. And then over here, I to the power 4 is just 1, so that just becomes x to the power 4 over 4 factorial. And then I to the power 5 is just I, so this is I times x to the power 5 over 5 factorial. And I to the power 6 is -1. It's the same thing as I squared, so it's minus x to the power 6 over 6 factorial, and so on. So it looks like we have some terms with no I in it and some terms that do have I in it. So let's group these terms. So I'm going to group here. Let me just duplicate this. So I'm going to group the 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial minus x to the power 6 over 6 factorial. I'm going to group those terms together. And of course, that keeps going. And what do you notice about that series right there? Let's actually start with that. Can you identify that series for me?
Well, it's all even stuff and it's alternating. I would hazard a guess this is the Maclaurin series representation of cosine.
Absolutely. This is just cosine of x. So I'm going to write this equals cosine of x, and I'm going to keep going. So now I'm going to group the terms with I in them, and I'm going to factor the I out. So I'm going to have plus I factored out. That's going to be x minus x cubed over 3 factorial plus over here x to the power 5 over 5 factorial. And or I guess this should be a minus because it's alternating, and so on.
eh?
Yeah,
It's like all the stuff. So and it's alternating, so maybe that's sine.
yes, this looks like the Maclaurin series for sine of x. So it looks like we have e to the ix equals cosine x right here plus I times sine of x right there.
This is my favorite equation.
Yes, this is a very, very important equation. It's known as Euler's formula. Euler's formula.
There's another very interesting result that comes from this, called Euler's identity.
Yes. So, but yeah, this is the one of the most important formulas in math, and a lot of things can be done with this formula. And like you said, one of the coolest things about this formula is e to the I pi. So you can plug in whatever you want for x because this formula is true for all x. But if you plug in pi, you get something very interesting. So if you have e to the I pi, so I'm replacing x with pi. This is going to be cosine of pi plus I sine of pi. So cosine of pi is just -1, and sine of pi is 0. So we have I times 0, and you're just left with e to the I pi equals -1. Very, very important identity. This is called Euler's identity. Yes. So
I should also mention that in pre-calc, you're often when you first like maybe algebra 2 when you learn logarithms, and like for example, natural log of -1, your teacher would probably have told you there's no solution to that. If you wanted to be kind of a smart aleck about it, you could use Euler's identity, and you can see that I pi is one of the solutions to that.
exactly, because the natural log and the e would cancel, and you'll be left with I pi. So that's the wonderful thing about this identity. This is arguably one of the most famous of all equations in math. And it's important because e is a real number, pi is a real number. I pi is not real, it's imaginary. But when you have a real number raised to this imaginary number, I pi, you get a real number. So it's you get -1. It's weird in some ways. And it's also very, very important because it's giving us a relationship between the two most important irrational numbers in math, which is e and pi. So so many applications with this. A lot of cool stuff comes from e to the I pi equals -1. And even if you were a hardcore nerd, a lot of the hardcore nerds tattoo this on their arm or on their back. That's how cool this identity is.
You haven't done that, have you?
Not yet. So that's how cool this is. So, but anyway, enough with the cool stuff. Let's go back and talk a little bit about Taylor. This will be the last part of today. So I want to go over a definition before I show you guys some stuff. So this is the definition of what's called a Taylor polynomial. Not a Taylor series, this is a Taylor polynomial. So let's say that f of x is a function, of course, and here t, the capital T stands for Taylor. It's T sub n. It's like T is a polynomial in this case. So just like a function right here, like p of x or f of x. So T is a polynomial. It's called a Taylor polynomial, and the subscript n means the degree of the polynomial is n, and the of x part means it's a function of x, of course. So going back to like the start of today when we derived the Taylor series centered at C, let me go back to that right here. That was an infinite series. But what we're going to do now is we're going to take the first n terms of this power series right here. So I'm taking the first n terms. I'm stopping at the nth term, and that's what's called an nth degree Taylor polynomial of f of x, centered at c. So this is f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared, and so on until you reach the nth derivative of f at c over n factorial times x minus c to the power of n. So we're assuming, that's our assumption here, is that f of x has n derivatives at c. So the derivative exists. Like the first derivative exists, the second derivative exists, the third derivative exists, all the way to the nth derivative. So for example, if you want to come up with a Taylor polynomial of degree 10, you want all the derivatives up to the 10th derivative to exist at c. So yeah, that's the idea behind a Taylor polynomial. So I'm going to highlight that. So yeah, you want to be able to plug in c into those derivatives and get something that's defined. So there's something very interesting. Like, let's pay very close attention to the first two terms of this series. Does this look familiar to anyone? Like from Calculus 1, what does that look like?
Like a linear approximation.
Yes, so that is the linearization of f of x at c. So note the first degree Taylor polynomial, that's t1 of x equals, it's those first two terms, so f of c plus f prime of c times x minus c. And it's the same thing as the linearization of f of x at c. So it's the equation of the tangent line at c, where, and this f prime of c right here is just the slope of the tangent line. So yeah, this is known as the linearization of f of x. And this is all from Calc 1. So if you have a function, you can do a linear approximation to that function near c. Okay, so let's say this is my function. This is y equals f of x. And let's say this is c right here. And this is going to be the first degree Taylor polynomial. This is going to, right here, I'm going to draw t sub 1 of x. So it looks like this. I like that. So this is t sub 1 of x. It's just the tangent line at x equals c. That's all t sub 1 of x is. It's just the equation of the tangent line at c. So, and it's good for approximating the function near c. You can see that when you're around c, this line is very, very close to the curve. So let's take an x value close to c. Like let's say right here, this x value that's close to c. I mean, that's not that close, but like I'm just kind of exaggerating here. But notice that the y value of the function, that's just f of x. Like, let me draw right there, all the way right there. This right here is just f of x. And let me make this dashed. All right. So that's the y value of the function. That's f of x. So the y value of the line is very, very close to the y value of the function. So here's the point on the line right here at x. And this is going to be t sub 1 of x right there.
It's pretty close.
Yep. So you can see that they're very close to each other. So let me write some stuff down. So t1 of x is the equation of the tangent line tangent line at x equals c. So when x is close to c, so for x approximately equal to c, we have that t1 of x is going to be approximately equal to f of x. So yeah, I hope that you guys can see that they're almost equal to the like that line is almost equal to the function when x is near c. So the Taylor series says that the function is equal to this infinite series right here. Let me go to it. So it's infinite. That's what the Taylor series says, that the function is equal to this infinite series. So as long as this goes forever, f of x is going to be perfectly equal to this, at least for like sine and cosine and e to the x. But we can see that f of x is going to be approximately equal to the sum of a bunch of terms. So this bunch of terms, it's called a partial sum. It's the Taylor polynomial. So you can estimate the curve, you can estimate the function using a line. That's what we did right here. But Taylor polynomials are going to make this approximation better. If I add the first three terms right here, you get a quadratic approximation instead of a linear approximation. If I add another term, you get the cubic approximation. So the more and more terms you have, the better the approximation. And eventually, as this goes to infinity, the series becomes f of x. So you can think of c, I said c is like the shift earlier, but you could also think of c as like the point of tangency. Like c is where the series begins to converge onto the function and it begins to look more like the function. So again, like if you have a curve like that right there, like this f of x right here, this would be the linear approximation. And quadratic approximation would look something like this. And then cubic approximation would look something like this, maybe. And but still, like C is the point of tangency right there. It's still centered at C. So C is where the polynomial and f of x basically become equal. And yeah, the closer you are to C, the better the approximation.
I'd like to mention something informally known as the fundamental theorem of engineering, which mathematicians hate, which is the identity, quote unquote, that sine of x is equal to x. This is an approximation that engineers and physicists like to use, but it's really just the first Taylor polynomial of sine of x, because the first term in the Taylor series or Maclaurin series of sine is x. And you can experiment with some values in your calculator and see that sine of x equals x is a pretty good approximation for small values of x.
Definitely. Yeah, that's a good point. Let me show you guys what happens when you increase the degree of the polynomial because I showed like linear approximations, but let's go to Desmos and let's do some stuff. So,
Love Desmos.
yes. So I'm going to graph the Taylor polynomial and the actual function. So let's do e to x. I have that up right here. And I'm going to write the sum of the first two terms for e to the x. So that was just 1 plus x. Let me do it in red. All right, so this is the linearization. So 1 plus x is the Taylor polynomial of degree 1. So you can see the graph of e to the x is in blue and the graph of the Taylor polynomial is in red. It's the line. So it's, it's just the tangent line pretty much. It's a tangent line at 0. So notice that the point of tangency right there is 0. So let's see what happens when you increase the degree of that polynomial. Let's add one more term. So that's going to be plus x squared over 2 factorial.
That looks a lot better.
Yeah, that's a quadratic function. And if you compare the two graphs, it looks like the graph of the polynomial became more like the graph of e to the x. And notice how the point of tangency is still at 0. That's the center. That's what I was saying earlier. The center is really just the point of tangency. And let's take a look at the third degree Taylor polynomial. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial. It looks like the graph of the polynomial is more like the graph of e to the x, better than before. And if you keep adding terms, the graph of the polynomial is going to become more and more like the graph of the actual function. So let me just go crazy. Let me add a couple terms. So x to the power of 4 over 4 factorial plus x to the power of 5 over 5 factorial plus x to the power of 6 over 6 factorial plus x to the power of 7 over 7 factorial. Notice how as I added more and more terms, the graph of the Taylor polynomial started to look more like the graph of the actual function, e to the x. So we can say that polynomial is converging onto the function e to the x. And I wrote out all these terms here. I wrote out 8 terms, and you can't even like differentiate between the graphs any longer for this like window here. Like you'd have to really like zoom in to like see the difference. So that's e to the x. Let's look at one more example. Let's look at cosine of x. So cosine of x, remember, is the sum of negative 1 to the power of n over 2n factorial times x to the power of 2n. So the first term of the Maclaurin series for cosine of x is just 1. So that's the first term of the Maclaurin series for cosine of x. So this is the Taylor polynomial of degree 0. It just 1. So looking at the two graphs, it looks like it's just the tangent line at 0 to the graph of cosine. So when x is near 0, the graph of cosine can be approximated by that red line. So now let's add more terms. So let's do 1 minus x squared over 2 factorial. So that's a parabola. And here, let me zoom out a little bit. And when you're near 0, the graph of cosine looks so much like 1 minus x squared over 2 factorial. And let's just keep going. So plus, I'll do a couple more terms, x to the power of 4 over 4 factorial, and then minus x to the power of 6 over 6 factorial. And if you look at the two graphs, now the overlap interval is even wider. So if you keep doing higher degrees, eventually you're going to reach a point where you can't distinguish between the two graphs at all for, for a certain like viewing window. So the more and more terms you add to this Taylor polynomial, the more and more the graph is going to look like cosine of x. And like I said, eventually you can't differentiate between the two graphs. So that's very, very, very cool stuff. So the higher the degree of the polynomial, the better your approximation for the function gets. And that's pretty much all I got for today. So I'll post the blank and the filled out notes in the description. And you guys can leave a comment with some suggestions on what you want the next video to be about. And I'll see you next time.
Bye.